This is Physics 30, Chapter 1, Lesson 7. This is the final lesson in Chapter 1. Today we're looking at relative motion, something that happens when, for example, in the picture here, you have a train that's moving, but you have somebody walking in the opposite direction. Their motion will appear different to observers standing on the ground as opposed to observers also sitting on the train. It would look like two different things. So we're going to talk about that. How do you suppose Homer would know that he is hurtling through interstellar space if his speed were constant? Well, this you can picture almost similar to us here on Earth. How do we know that we are hurtling through space at some immense velocity, even though our velocity is constant, right? We don't really feel like we're traveling through the galaxy, but yet we know we are. Well, simply speaking, without a window, he wouldn't. All of the laws of motion apply within his frame of reference, meaning inside Homer's spaceship, all of the laws of motion apply, and he would have no way of knowing that he's traveling. Same thing here on Earth. This brings us to the conclusion that all motion is relative. It depends on what you're measuring things according to. The only way to define motion is by changing position. The question is changing position relative to what? Are you in motion right now? Well, this has multiple answers. You are moving at about 1,000 miles per hour relative to the center of the Earth, just based off of the Earth's rotation. We also know that the Earth orbits the Sun, and the Earth is hurtling around the Sun at over 100,000 kilometers per hour. So maybe that's your current motion, that's your velocity. So depending on what your frame of reference is, we have different velocities. If you're sitting in a chair right now, we could say relative to the Earth, your motion is nothing. However, relative to the center of the Earth, because of rotation, you're moving quite quickly. Relative to the Sun, or the Milky Way galaxy, you're moving at over 100,000 kilometers per hour, which is extremely fast. So the answer to are you in motion or what's your current velocity really depends on what you're measuring it according to. All of these answers are equally valid. An example. A train is moving east at 25 meters per second, and a man on the train gets up and walks towards the front at 2 meters per second. What is his velocity? Well, it depends on what we want to relate his speed to. If we're comparing his speed to somebody else sitting on the train, we would say that his velocity is 2 meters per second. Since he's walking at 2 meters per second on the train, if you're sitting on the train as well, he will pass you at a rate of 2 meters per second. However, if you're standing on the ground outside the train, we would say that his velocity overall is 27 meters per second, because the train is already moving at 25 meters per second, and then the person is also walking at 2 meters per second on top of that, meaning overall, from our perspective on the ground, it would look like he's moving a total of 27 meters per second. Another example. A passenger on a 747 that is traveling east at 230 meters per second walks towards the bathroom at the rear of the airplane at 2 meters per second. What is the passenger's velocity? Pause the video here for a second and see what you can come up with. Again, answers depend on what we look at and what we compare it to. Relative to somebody on the plane, the passenger is walking negative 2 meters per second because he's walking backwards towards the rear of the plane. However, to somebody outside of the plane, somebody on fixed Earth, we would have the plane is traveling at 230 meters per second, but then the person's walking backwards at 2 meters per second. So overall, to somebody on Earth, it looks like the passenger is moving at 228 meters per second. What happens to the aircraft's forward speed when the wind changes direction? Well, if there's no wind, the plane moves with velocity that comes from the engines. It's simply propelled directly to the right in this example. If there's some velocity of wind moving in the same direction as the plane, it adds to the overall velocity. This is how planes can travel sometimes quicker certain routes if the wind is in their favor. And it makes sense. The wind is pushing on the plane, helping it to move quicker. When the angle of the wind changes, it's still giving the plane extra speed, but is also pushing it south. Remember that every vector that is at an angle, such as the red one here, will have an x component and a y component, a vertical and a horizontal component. So the part of the vector that is moving to the right will still help push the plane forward, making it overall faster, but the part of the vector moving down here will also be pushing the plane off track. So it will be moving quicker overall than if there was no wind, but it will also be being pushed slightly off course. If this wind is completely perpendicular to the plane, the wind is not having any impact on forward movement. It's not slowing it down, but it's also not speeding it up, but it does continue to push the plane south off of its track. If the direction of the wind continues to change, now the wind is still pushing it south and off track, but it's also somewhat slowing it down, whatever that x component of the vector would be. And when the wind is directly head-on, wind is now working against the aircraft thrust, slowing it down, but causing no drift. It's staying perfectly on track, but it is being slowed down by the wind. Perpendicular kinematics. Critical variable in multi-dimension problems is time. So we already talked about this slightly, or for a little bit in the other lesson when we were looking at projectile motion with the soccer ball. Even though we considered vertical distance and horizontal distance differently or separately, we know overall there's only one time because the ball only got kicked once. There is only one scenario, there is only one measure of time. We must consider each dimension separately, using time as the only crossover variable. So we can consider vertical and horizontal separately, or we can consider different directions separately, but time is the variable that will be the same in all situations. So consider the example of a swimmer moving at 0.5 meters per second, swimming across a river that is 200 meters wide. The question is, how long will it take the swimmer to get across? Well, time will simply be the distance divided by velocity. So in this case, the time would be 400 seconds. This is important because we need to remember that time is constant as we consider different scenarios. So this 400 seconds assumes that the river has no movement, there is no friction with water, there is nothing holding the swimmer back. So of course that represents kind of an ideal world that we know doesn't exist, but in a perfect world, in absolutely still water that does not slow the swimmer down at all, they would cross the river in 400 seconds. Now, assume that as the swimmer moves across the river, a current pushes him downstream at 0.1 meters per second. The time to cross is unaffected. It's still the same. The swimmer still arrives on the other bank in 400 seconds. So what is different? We know that now we have introduced a current, so something has to change. What is it? It's the arrival point will be shifted downstream. So because the swimmer with no current would simply cross directly across and arrive here on the opposite bank, when a current is introduced, their arrival point is shifted downstream, meaning their distance to cross becomes longer. We know in any right angle triangle, the hypotenuse would be the longest side. So the distance they have to swim is longer. However, this horizontal component of this has also increased their overall velocity, so they actually still make it across in the same amount of time. Their position is just shifted down. So how could you account for that if you wanted to land directly across the bank? Well, you could calculate how far downstream you're going to land, and whatever angle that would be, whatever angle you're going to end up downstream, If you set off for the same angle upstream and actually head upstream instead of going straight across, the current will push you down in the same way, so that as you angle upstream, the current will push you down, landing you directly on the opposite bank. This is what's expressed in the two pictures below. If you want to land an airplane in some city but there's a strong wind, you just angle your plane up so that as it travels, the wind will push it back down to your landing point. Same thing with the boat. If you angle in one place, the current will push you down and you'll end up somewhere else. So for some practice, we're going to look at page 49, numbers 2 to 4 and 6 to